CLI and a cross-platform IDE for C and C++. Download now.
Welcome to everyone. Today I want to talk about challenges that we have in safety critical systems when it comes to dynamic memory allocation. Basically, I come from BMW, and very often I have the discussion with the colleagues about like, hey, why we cannot use dynamic memory allocation? What are the problems with it? And this would be like the answer. Like the goal of this presentation is that you are aware of these challenges. A bit about me. I've been working in C++ for quite some time now, and I've been since 2018 by BMW working in safety critical systems, and I also represent the company in the C++ committee meeting. I do my best there to contribute as much as I can. And I'm also in the MISRA working group. I'm not so sure how many of you heard about MISRA. These are rules for safety critical systems. And there is, yeah. But let's first of all get started. How many of you are not allowed to use dynamic memory allocation? 1, 2, 4, okay. How many of you do not know what are the issues about dynamic memory allocation? Okay, it seems that most of the people know about the issues. Let's see if at the end they believe the same, that they knew all the issues or not. First of all, like sometimes there are some misunderstandings, and we should start with defining what is a safety critical system. Basically, it's a system whose failure could lead to one of the following. Could be a loss of life or serious injuries. It could lead to significant property damage, buildings, you name it, or could lead to significant environmental damage. And if we want to grab some examples to make it a bit easier, we could have a nuclear power plant in Italy, right now retired. We have this super cute plane from Airbus to transport planes. It's a plane to transport planes. And then here we have an X-ray machine that they were using to remove my wisdom teeth. All of these would be significant safety critical systems. Now, when we are in safety critical systems, you will hear a lot about functional safety. And this is something that has been going on the last 1-2 years, talking about safety in the C++ community. And there's not well understanding what we mean when we talk about safety. Safety has a very wide range of meanings. And in safety critical systems, we care about functional safety. What is that? To keep it short, it's protecting a user from technology. That's what we want to achieve. We can put it a bit longer. Systems that lead to the freedom from an acceptable risk of injury or damage to the health of people by the proper implementation of one or more automatic protection functions, often called safety functions. A safety system consists of one or more safety functions. Let's do the same. Let's grab some example. You all have at home probably a kettle, and there is certain safety in it. You might not have think about, but it's there. First, we have an automatic switch off to prevent, and the goal is to prevent that you might have some burning risk. We have the boil dry protection. If it runs out of water, it will automatic switch off. You want to prevent from some fire hazard that goes into flames or something like that. And then, last but not least, you want to avoid that the splashing of boiling water when you pour it, and usually they have some mechanism. All of these are mechanisms in order to achieve this functional safety, that the user is safe. And as you see here, doesn't talk anything about which programming language is someone using inside. Is it using Java? Who knows? That's the implementation detail. The user does not care. Now, in this kind of environments, it's heavily regulated. You need to pass certifications, and then usually you need to show that you follow certain standards. We have one standard to rule them all. This is the one here. If you don't find a better one, that's a good starting point. The thing is that then each industry has some specific problems, and then multiple standards has been appearing. You have for industrial processes, machinery, nuclear power plants, they have their own medical devices, automotive, and railway. And today we'll focus a bit on automotive. Is the one that I'm working on, is the one that I know a bit. I'm not a safety expert, but this is the one that I'm familiar as a developer. I didn't mention it. It's like I'm not on the safety team. I'm basically a software developer. I'm the technical lead of my team, and I just have to deal with that. That's how I got to know it. Basically, then, in this, when you have a safety critical system, the first thing you have to do is to assess the criticality of the system. In this ISO 26262, we have multiple categories. We have severity, that basically it's like if something happens, how bad it is. We also have exposure, that basically means how often or how frequent you are exposed to that situation. And then basically we have controllability, like if something bad happens, how hard or how easy it would be to control. And now, based on that, we could have a table that's this is the table that is on the ISO, and basically tells you how critical is the system. And the important part here is that basically you have the letter D. This would be the most critical part. That's like it's you are exposed. The exposure is really high, and basically the severity is high, and it's like it's hard to control. And then from the lowest, that would be this QM. Now in the standard, for you to understand, then basically like in this standard, you have some tables. The standard is full of tables that tells you what you should do, what you should not do. And they have this marking with double plus, plus, and O that basically tells you like if it's highly recommended, recommended, or not recommended against, or not in favor, nothing, like you can choose. And then basically depends on the criticality of the system. It tells you if it's high recommended or not, or what to follow. And this already gives us an impression that depends on the criticality, you will be more or less restricted. I will walk you through a bit on the standard for you to understand what our requirements from the standard point of view, from regulation point of view. This is important because when someone tells you you cannot do that, you need to understand what is the regulation tell you. But I will keep it short, and I will keep it like quite concise. Basically, in this standard, we have it's a standard full of 12 parts, and there's one part that's the one that we are all caring about, that is the software development. This is the part 6. And that is structured in several subparts. The first one is general software development, and there we'll already start seeing these sections. And basically, what it's telling us is that it requires the use of coding guidelines. And this is the first point where we see, okay, we want to use coding guidelines. It tells us to use language subsets to exclude certain language constructs. We should not use everything from the language. And basically what we want to achieve is like we want to avoid constructs that can be interpreted differently by different developers. Doesn't mean that it's good or bad, but if we have a different opinion of how it works, that might be potentially dangerous. Experience tells us that leads to mistakes. If you do that, usually you have problems, then we should avoid that. Or can lead to unhandled runtime errors. Then we have the second section. This is software architectural design. And there, what it talks about is that we want to avoid systematic faults. And to do that, we want to consider appropriate management of shared resources. Then if we move on with architecture design, now it comes unit design and implementation. And in that section, what it talks about is we want to ensure that we have like correct order of execution of subprograms and functions. And we want to have a correct data flow and control flow. And how to do that, it guides us and tells us, okay, you should not have dynamic objects or variables. That's hard usually on the control flow part. Or else online test during their creation. It also talks about avoiding global variables or justify their usage. It doesn't tell us not to use them, just justify it. And no hidden data flow or control flow. And then we have the last section that will be about verification. And basically for that, it's the goal is to have unintended functionality. Like everything that we put there, we want that it's a conscious decision. That's the functionality that you want. And you need to have sufficient resources for that. If not, you might have issues. And then it talks about how we can test that. This is what a standard requires. And maybe the main point here is about using guidelines. Now let's see what we have in the world with the standards, with the guidelines. Basically, if we grab one of the first guidelines for C++ on safety critical system, we would find the Joint Strike Fighter for C++. This was developed by Bjorn, was used on this Joint Strike Fighter project. Then we have the AutoSAR guidelines. These are from automotive. These guidelines for C++ 14. And then basically we have the latest MISRA 2023 that is for guidelines for C++ 17. All of these are guidelines for safety critical systems. And now let's see what they have in common when it comes to dynamic memory allocation. The first thing that they tell us is like, do not use dynamic memory allocation. That's simple. We don't use it. Bye. That's it. But they do not stop there. Like you have, do not use dynamic memory allocation after the initialization phase. And this is an important distinction. It's not the same if you have an error in the moment that you start the car than if you are driving 130 kilometers per hour on the highway. Or the same with a plane. One thing is like you just lay at the airport or you are on the fly. And that's an important distinction. And if you have to, they provide guidelines. Like even if you have to do that, then it's like, okay, here you have some guidelines, and I'm trying to guide you on how to do it in the best way. But the most important is that most of these guidelines, they have a rationale, and they tell you why. And these are like the important parts to keep in mind. First, we want to achieve that we do not have memory leaks. Why? Because we also want to make sure that we do not run out of resources. We want to avoid out of memory. We want to avoid allocation-deallocation mismatch. We will see a bit later what that means. We want to avoid memory fragmentation. And this is a part of also that we want to avoid non-deterministic runtime. It might be important that you have really deterministic runtime in some use cases. And you also want to avoid the use after free. These are like the 6 main themes that they will appear everywhere. And this is the things that we want to avoid. Okay, now we saw the standard. Now let's go back to programming to our world. And the first thing that I would like that you all think about, what is a program? And I could not find a definition that I was liking enough. And I came up with this sentence on my own. And the thing is that for me, the program, it's nothing else than a bunch of instructions modifying chunks of memory based on some inputs to provide some outputs. If we think about that, it's not much more than that. We have a computer. The computer will execute some instructions. For that, it will need some memory. It's a bit what John said. I mean, the vector is nothing else that you need to put the data somewhere. You provide some inputs, and you generate some outputs. That's the program. Now, we need to generate this program. This program, it will have to run, right? But before we run the program, we need to have it. The first step, we have a bunch of files, headers, CPP files. We feed the CPP files into a compiler. This will generate the output files. We feed them in a linker, and then we'll have the executable. in Linux will be the elf file. Okay, now we have our program ready to run. And we have it in the machine, and it's a stop. Now, how do we run this program? This is also something we need to keep in mind. We have several steps. The first step is like it starts. But now here comes the first thing, that we have implicit loading of dynamic libraries. Then once this is done, the program goes into a running state. And then during the runtime, you could decide that you want to explicitly load some additional libraries. Okay, so far so good. Let's take a look to how it looks like the program. The examples that I will show, I mean, you can find them on my GitHub. I put some QR codes. From one of them, you can get to all of them. Now, basically, what do I have here? Here, just a program that does nothing, but I just put some globals. And what I want to show you is how these globals then, how all of this data ends up in the program. In Linux, you have it quite easy to do. You can use the readelf tool. And basically, to the readelf, you can just provide a binary. And then you have several parameters. You have one parameter that is --all, that will give you all the information. But now, for the moment, let's check only on the sections. If you say sections, then what you will see is like you will find a table like that, slightly less formatted. And basically, here shows you like all these bits and bytes that they end up in your program. And the first thing is that the sections in your binary, they have a name. This is nothing else than for helping the human. The machine doesn't need that at all. Then basically it tells you an address. This is the address on the binary. This is just the binary. We didn't load it in memory yet. Then basically we have a size of the section. And later we have some flags. And what are these flags? Basically, we have here a section that tells us like if it's writable, executable. It tells us the nature of these sections. But here, for the moment, we do not know anything about where are our variables. There's no information here. If we call readelf, but with symbols, then now this is when it starts getting interesting. Here you have this list of this table. And basically, in the name side, you can find the symbols of your program. And I mean, in C++, because we have the mangling, you need to just try to remove from your brain this underscore ZL3. But basically, you can see in the last rows that we have this SC-foo. And basically S-bar, SD. But still, this shows us the variable, but doesn't really tell us where it is. Not completely. We have this column that is the index. Not sure why they started with n, but it's like the index. And this number, it's an index to the table that we just saw before. Okay, now for a bit of simplicity and to make it like easier, I just did the mapping for you. What do we have? Okay, the first thing that we have is that the strings, they will end up in this data relocation read only. Then here we have these integers, global integers, uninitialized that will end up in this BSS section. We have these ones that are initialized that they go into the data section. And then we have these constants that they end up in the read-only data section. And our main would end up in this text section. And this should give you an overview of how things they end up from your code to memory, to the the memory of the executable, like in disk. Okay, now we want to load the program. And what we said is like, a computer is nothing else but instructions and memory, right? Basically, we have this self binary, and now basically what it does in the first step of the starting, it just do the mapping. And basically like this, you have these memory sections. Basically like on memory, you will see in certain memory addresses, you will have these sections created. And basically in these first two sections is where it goes most of your code. And basically you have this R minus X, this is like the permissions, and you have one that you have the Rx is all your instructions and read only, and the write is the part that you have to write about. But then additionally, then here we start seeing some new things appearing on memory. It's not only what you were putting in the binary, more things start appearing. You have this VVAR and VDSO. These are kind of special sections to deal with the operating system. We will not go into detail today. We also find that there's one section that the dynamic libraries, they start loading, and one that it loads, that needs to load is basically the loader of dynamic libraries, because that's the one that you will then later use. And we have the heap. And that's it. That's what we have. Like if you grab GDB and you stop on the first instruction, what you will get in this program. Now we are reached on that picture on the first step, on the starting. And now here, like, okay, we go into the running state, and basically what it happens is that this main section first already gets divided into segments, two memory segments. And we start seeing some other dynamic libraries being loaded. So this is like more memory that's being used while loading. And one would be the standard library. We also see that appears a new section, that it's the heap. And what we'll see when we run is that the heap will start growing in this direction, downwards, and the stack will start growing on this direction. And this should already just give you a view on how now, what do we have in memory? Now you should have this vision about, okay, this was my executable, now this is how it looks in memory. Okay. Let's go to the next example. What we want to see now is what happens with the stack and the growing. Who can tell me what this compute function is doing? You provide a number, and it gives you a number. It gives you the same number. It's probably the most stupid way to calculate the identity of a number in a recursive way. And basically what, if we load this into memory, we will see that if you started with GDB, then basically you can just, this is started in GDB, then you can do the info proc mappings that you see at the top left. And you see all this, how does it look, this program, into memory. You can see that the first two are the main, and basically like this is a little bit what I described in the previous example. And here we see the stack. And we also see the size of the stack, it's 132 kilobytes. Okay, now what do we do is that we have this stack, 132 kilobytes. Let's put a breakpoint here on the return 0, basically like on the deeper of the function. And let's ask, we want to compute the 20,000. What does it happen when we have the breakpoint there? We reach that point. The stack could not handle such a big, and the stack grew. And now the memory segment of the stack is at 632 kilobytes. Here we already like expanded the memory that we are using. Okay, and this is like iterating. We have this loop here, and I ask for the next number, I enter a 0. What will happen if now I check the stack what will be the size of the stack? 0 would mean like we already unwind the full recursivity function, and we are just more or less back at the same level. What it happens is that the stack stays exactly the same. The stack doesn't shrink back, like it was expanding, but stays there. That's the first thing that you could decide how much it surprises you or not. This is how it works. Okay, now let's see how it works with the heap, because this is another way that we can get memory. What you will find in this repository is a program that basically tasks you for actions that you want to do. And basically what you can do are like several things. You can basically say, okay, I see that here it got cut, because basically like you can allocate. You can decide that you want allocate, you want to deallocate, or you want to print the pointers of all the allocations. And basically also this program, what it does is at the very beginning, in a programmatic way, you can just introspect these sections of the program. And basically what it prints is like this, it searches for the data segment in memory that is called heap. I mean, we saw it has a name. And basically what we do is to print this information. We are printing the size of the heap, and we show where it starts and where it ends. And now it's basically what you can do is like you can say, okay, I want to allocate 50,000 bytes. This is what we will do is like to create an array with a unique pointer, just grabbing 50,000 bytes. And what we see is that the size of the heap has been growing. Now it's like 270,000 bytes. Makes sense, maybe, or not. I mean, if we see it was 135, 50,000 should fit there. It grew. Was it expected? You decide. Okay, now we have 50,000 bytes allocated, and I want to allocate 100,000 more. And in total, we have already allocated 150,000 bytes until now. And we see that in this case, it didn't expand the heap. We are still at 270,000 bytes. Okay, let's go a bit more ambitious. Let's try to allocate a bit more. We allocate 200,000 bytes. It means that until now would be 350,000. And we look at the heap, and we see that we have 270,000 bytes. How can this be? Yeah?
It allocates via mmap.
It allocates via mmap. Yes. The other option would be like some people could think about. People have heard in Linux about this lazy allocation, right? And that's why I added here on the program also you have this random initialized memory that basically like everything that we allocated, we just give a value. But no, that doesn't change anything. The issue here is that on the direction that you pointed. And how we can figure out that? Okay, we print the pointer of the addresses. And basically what we do is like, okay, we see that the 50,000 bytes that we did at the beginning and the 100,000 bytes are in a very similar addresses. And these addresses are falling into the heap section. What I'm doing here when I print, basically the program what is doing is you just convert the address to a hexadecimal, and then you search in which section that falls. And we see that both they fall into this section called heap. But we have the last one that is the 200,000 bytes, and this does not end up into the heap. It's a section that doesn't have a name. And we were not really so aware of that. Why is that? What does it happen when we do a make unique? And this is what the program is doing. It's just doing a make unique. We do make unique, and the make unique will do a new under the hood. And the new what we'll do is that we'll do a malloc under the hood. And now here comes what does the malloc do? Well, you have multiple options that the malloc can do. It could be that does no operating system call at all. It could be that it calls brk. This is the call that basically it's to expand or to change the size of the memory segment. Or it could be that you do an mmap, that basically just to get a full new data segment. And why this is happening? Basically, the first thing that here you need to keep in mind is that the behavior of malloc depends on the implementation. This is nothing that the standard says anything about. And basically, this happens because there is this link here that's very interesting reading before going to sleep. This is like it talks you about how malloc works, and basically the idea is that you have different arenas and different heaps, and basically like you have some different links list in the end, and that's why we saw that a new heap appear, a new memory segment. And what I want to show with you with that is like, not so sure up to this point how many of these things were surprising you or not, but this is the first part on the, let's say, dynamic memory. You could discuss if the growing the stack is dynamic or not, but that grew is happening dynamically, right? It was depending on my inputs. And this one level. But now let's see, what do we have? Like, what do we have under the hood on our hardware? Well, on our hardware, then we have, usually the architecture that we have is something similar to that. We have some cores, and each core will have some CPU registers, and then we'll have also different cache levels, L1, L2, L3, some RAM, some disk, and a memory controller. And when you try to get this memory, you might end up in cache misses, having to go to find things in RAM or in disk. And to get an idea of the order of magnitude of the time, basically, if accessing the L1 cache would be time 1, unit 1, L2 is 4 times more expensive, L3 is 40 times more expensive, RAM it's 80 times more expensive, and disk is around 10,000 times more expensive. I hope I don't miss a zero. This is like the implementation part. But have you seen, do you believe that Heap is in the standard or anything like that is in the standard? Now the thing we need to understand is like, what is it in the standard? What do we have in C++ in this topic? The standard has just a mental model. And in this mental model, you have objects and storage. And how it works is that if we grab this axis, and this would be just the timeline, we have some a storage that basically like the lifetime of this storage starts. And then at some point, the lifetime of this storage will end. And then in the middle, you can do things with the storage. You could construct an object on this storage, then the constructor starts, and then at some point the constructor ends, and this is the moment where the object lifetimes begin. When the object lifetimes ends, this is at the beginning of the structure, and then the structure finishes, and you are done, object is gone, but you still have the storage, it's still there. This is the simple case. Maybe even more simple would be that the storage starts at the same time when the constructor starts. But we have other cases. You have cases where you could reuse this storage, where you have first an object, and then the lifetime ends, and then you have a second object. Or you could have things like you start the constructor, the object lifetime starts, and without calling the structure, another object starts. This is perfect C++, this is totally valid. Probably it's not what you want. Probably you really wanted to have the structure call, but this is perfectly fine in terms of the standard. Okay, what did we see so far? we touched several topics, but where I want to go with that is like, let's revisit which type of storage we have in the standard. We saw the implementation, but what do we have in the standard? We have static storage duration, we have thread storage duration, we have automatic storage duration, and we have dynamic storage duration. The automatic storage duration would be the stack. The static storage duration, we know it's the globals. And obviously, the dynamic storage duration is what usually we call the heap. And I just put a note here because we have this special situation that exceptions go separate. They just use the phrasing, I do not remember exactly, but it's kind of like, it obtains the storage in implementation defined way. It's a special exception storage. And now to close the circle with what we saw, if we saw this object in like the program in memory, basically this part would be the static storage duration, this part would be the automatic storage duration, and this part would be the dynamic storage duration. And for this talk, I completely omitted the part of the thread storage. That would be something that it's quite similar, but I just didn't want to add more complexity. Okay, now let's start with the C++ quiz. New and delete expressions can be used to allocate and deallocate object on the heap. This is how we can do it in C++ to get heap allocation. And now here, how many forms of the new operator are available in C++? How many? Infinite? At least 3? Okay. We have 8. They are duplicated for arrays and non-arrays. What about the delete? It should be simple, no? I mean, it's like if we have 8, it should be 8 also. No, 12. You have 12 forms of delete. And they are replaceable. What does it mean is that you can just provide, like if you don't like the one that comes with it, you just provide your own. And then we have new and delete expressions. And the new, we have 2 forms of the new expression, where you can have like this type ID with parentheses or not. And then the delete has 2 forms, like for the, and I think I missed the braces. Okay, the new, I missed the one of the arrays. Not so relevant for the part, but let's analyze what are the parameters of the new that we saw, the new function. Okay, on the new function, we can see these 3 types of parameters with combinations of them. The first parameter is the size. It's how many bytes we want to allocate. The second parameter is asking like, what is the alignment to be used? And the last parameter is to say we do not want to throw when there is not enough memory. There's an option to allocate without throwing. Okay. And how we can allocate an integer? Quite simple. We call new. And we have these different forms. You can put the parentheses or not. You can provide an initial value or not. And the initial value, you can do it with parentheses or braces, whatever you like. And you delete with the just delete p. That's it. For arrays, it's a similar approach. You can have the size of the array that you use from the initializer. And then basically you can also have them uninitialized. And the important part here is that the delete needs to go with the brackets. Otherwise, you have problems there. If it's not an integer in just your class, quite simple, it's the same, just replace int for your class, not different. But all of these forms, they can throw a bad alloc when there is not enough memory. Okay. Now, now we saw how we can do it. Now, which of the new will be selected if we have this any of these constructions that we want to allocate an integer? We'll have to pick one. The second. It could be the first one or the second. It doesn't matter. And that's something that is like, it doesn't matter. Like, it's implementation defined. Like, it could go with the one with alignment, or it go without the alignment because there's no special alignment requirements. And for the delete, which delete version will be selected? Here we saw we have more options, 6. Basically, any of these 4, basically. Okay. We saw that before we could throw an exception, but we want to do it without throwing. For doing it without throwing, we need to use the expression that is with the placement new. And what we can do with that is that we put in the placement new part, we can put this a stood no throw. And basically, this is the way to indicate that we'll not throw. And then which of the new will be selected? Any of the last 2. Same reason, like it's a no throw, and it's could be with alignment or without. Okay, and then basically we had it allocated with the no throw version, and now we just go there and we just decided to delete it. Which of the new version? Okay, I said new here should be delete. Which of the delete version will be selected? Not the no throw version. It's any of the first 4, but not the no throw version. And it doesn't matter, because what does it mean delete to be no throw? Cannot delete throw. And here we can already see the first hint. Like, the delete expression doesn't have a corresponding placement new delete. Like, there's no way that you could know that that delete wanted to go with the no throw. You cannot deduce it from the type of P. Okay, now how can we do it with the alignment? We saw that we have some operators that goes with alignment. Maybe I just want to put with a special alignment, right? Okay, we can do that. We can just use the same. We can use the placement new expression. We provide on the parameter. We provide the stood align. And we say that this integer should be aligned 64. Can we? I don't know. Let's ask the compilers. GCC says that yes, we can do that. Clang also agrees on that. But MSBC says that it's a bad idea, that you should not do that. Or doesn't want us to do that. And what we get? We get this nice error that basically, like, usual deallocation function, blah, 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 would be chosen as placement deallocation function. The usual one. And you see that in the usual one, void pointer, align val t, but that's what we want, right? Okay, let's see what happens in reality. Which here would be selected. Okay, we create the new, and it selects the one with the align. That makes sense. I mean, this requires a special alignment. And in the delete, which one will get selected? Oops, it selects the one without alignment. It's kind of, it feels a bit like of a mismatch, right? And we could also then combine it. Like, the thing is like this. So this function new and delete, you have multiple parameters. These are the parameters that you put in the placement new. You could just add alignment plus no throw. It's like, we want a special alignment and no throw. Can we? Well, ask again the compilers. Oh, now MSBC is happy about that. Well, it seems that we just fool MSBC because we still have the same problem that we are not selecting the delete with the corresponding alignment parameter. How do we have to do it for doing with alignment? That's not the right way, even though, like, it has the feeling that it works, and with GCC doesn't complain. The problem is that in the moment that you delete, you have not that information, unless this information is part of the type. If you really want to allocate something with a special alignment, just forget about adding the alignment request when you do the new. You make it this part of the type. If now we have this class foo, and we say this is aligned as 64, then we do the new, and then this will just select the one with the alignment parameter. And also for the delete, because the delete knows about the type and knows that the type has the alignment. That's the right way to do it with the alignment. And if we want to do the no throw with alignment, then yeah, we can pass the no throw in the placement new part of the expression. And then basically this works as expected, I would say, except it doesn't call the no throw. Why do we have the no throw into the delete then? For new expression. Can you elaborate on that?
Will fail to allocate stuff, then the placement leave will go in the new expression.
If new fails to locate, almost like if the initialization on the new would fail, like if the constructor would throw, then the delete. But yeah, like basically it's like in the moment that when you do the new, that would potentially fail, then basically the exact matching will get selected. And that's the only reason why we have it there. Not really that, but it doesn't have play a role. What is important here is that you need to keep in mind like what gets selected. And the best way to avoid that is just do not come up with fancy things that they do different semantic, like that the semantics is different. I mean, in the end, all of the delete should be the same thing and all the new, they should do the same thing. Okay. Now we saw how we can allocate memory dynamically with the core of the language. But what about the C++ standard library? What are the mechanisms that we could end up with dynamic memory allocation? Well, we are based on C. We can just grab the C API. That is there. Like we have it exposed. We can call malloc, calloc, realloc, line alloc, and we can free the memory with free. That would be one option to end up with dynamic memory allocation. We could also use the smart pointers. That's also a way that you will end up with dynamic memory allocation. And in C++ 26, we will have indirect and polymorphic. These are two new types that it's nothing else than heap, like it's to put objects allocated on the heap, but with value semantics. Like you just use the normal value semantics, but they are going onto the heap. It's just to force them to go to the heap. You have the implementation here. We will not go into detail into that, just for you to know that that would be something that it will heap allocate. But these are kind of like obvious situations. What you saw right now, you are explicitly asking for dynamically allocated memory. Like you are explicitly asking for heap memory. But now let's go to the in the standard library. Like, let's play a game. The game is called, does it dynamically allocate memory? And how much? Make unique of an integer of 2. Does it allocate? Yes. How much? 4 bytes. In my machine, right? Make share. Does it allocate? Yes. How much? 24, correct. Because we have the control block there that needs to be allocated also. Stud string, the smallest string. Does it allocate in my machine? In my machine, no. What about a big string that does not fit in the screen? It allocates one allocation, 62 bytes. I also put you here the QR code. You will then have the examples there, and you could also extend it if you want. What about a string view of a string that does not fit in the screen? No. That goes on to the static storage. What about an stud array? Correct. What about a stud vector default constructed? No. What about a stud vector of 8 elements? Yeah, sure, 32 bytes. What about a stud function where we provide this function that basically this function does is like, or you give it 42 or just terminates? No. Okay, let's push a bit the limits of a stud function. Now basically we put the function, we have a struct called universe and has this member function. And basically what we do is that we create this object universe, and then basically we do the stud bind with the member function and the object. Does it allocate? Yes, it allocates. In my machine, 24 bytes. Now we want to create a thread. Does it allocate? Do we care? Probably you have more issues if you are creating a thread. Yes, it allocates 24 bytes. But we learned that stud threads are not so nice, right? I mean, we should use JThread. Does it allocate? Yes. How much? The same? More? 48. Why? Yeah, stop source, exactly. Okay, we want to create a promise. Does it allocate? Yes, it allocates. It already grabs all the memory. What if we want to call get feature on a promise? No, we already did everything on the promise. What about if we want to set the value? No, I mean, we already paid for it. And if we create a feature? Also no. Stud any, 42. No. A stud any with a smaller string. No, no, yes, no. No, yes, 32 bytes. But with a smaller string, but it allocates. Stack trace, this is quite fancy. This comes in 23, I think. You can just get the stack trace and you just call current. Does it allocate? Quite a bit, 512 bytes, at least in my machine. Okay, and now basically we just saw a little bit what the ISO standard says. We saw what the guideline says. We saw how we can allocate, and we saw how allocation happens. But now if someone tells me like you should not use dynamic memory allocation, I mean, the first thing that you want to know is like, how can you know if something dynamically allocates? What are the ways to know about that? And I would love to have like an answer that works for everything, but let's see what we can do with what we have. The first thing is that you will find in some places in the standard, the best is just grab CPP reference that talks like about class satisfies allocation aware container. And this already like, if you end up in a type that talks about allocation aware container, then this is already the first hint, like this might allocate. Okay, second hint that we could have in the library, when we have basically a parameter that is called alloc. Like when you have this templated parameter that's called alloc, this is like alloc from allocator. That's the next hint. We'll also see in some places where it talks about throws but alloc if memory could not be allocated. Like if you are in C reference, you could see something like that. And it's like, aha, that gives me a hint. It could be that you don't have the alloc parameter. It could be that doesn't satisfy the allocation-aware container. But if it tells you that, then you know that an allocation might be happening. What other options we have? Well, if you are an expert, if you already tried to implement that, and you reach the conclusion that the only way to implement that is dynamically allocating memory, then you know that that functionality will probably also dynamically allocate memory. You have another option that's a bit more reliable, that is like you could provide one of the replacements functions that we saw, and there you can do some kind of logging, you can do some kind of terminate, and this could give you a hint on like, this is allocating. These are like the ways that you have. Like there's nothing else in the standard that tells you how to, like, that tells you this will for sure allocate or this will for sure not allocate. I find it unfortunate, but that is not there. The good side is that this leaves side to the implementers. Okay, but we can customize dynamic memory allocation. Which options do we have there? The first option that we have is with the global new and delete. We can do something like that. Basically, what we saw in these global functions is that they are replaceable. Replaceable means that they are replaceable at link time. And you can provide your own implementation. And you can do whatever you want there. In this case, we are just basically mimicking the standard with small difference. What's the problem here? We have one new and delete to rule them all. Like all types, all allocations will go through this function. And we saw from the parameters here, you do not have any information about the type. As we saw, we have multiple overloads, and they should follow the same semantics. If you define that one, the best thing that you can do, if you define one, define them all. We saw you have 8 or you have 12. You can define one based on the other ones. That's totally fine. But if you define one, define the other ones, because maybe today this is selected, then you change the compiler, another is selected, or you upgrade whatsoever. Follow the same semantics. It replaces the default version, the one that the implementation would have to provide. And once it is replaced, there's no way back. Like you cannot say, from here I call the original new that was there available. That's not an option. This makes it a bit hard if you want to just do tracking memory allocation because you cannot call the original new. And basically, like all of these new and delete, they have certain semantics. And if you do not follow them, basically the behavior is undefined. Then you have undefined behavior. Everything built on top relies on certain semantics that you have to follow. We have another option to do that. We have a class new and delete. I was not even aware of that one. But basically, when you have a class, you can define a member new. And basically, what does this mean? Like you can, the same principle, you can do whatever you want there. And then basically, like it customizes the new and delete per type. Then it's like this type will always, when you do an allocation of the type on the heap, it will call this. This means that if you allocate that on the stack, well, that will not get called. It means like, do not try to hijack this for fancy things like counting how many objects you have or stuff like that, because then you would miss all the ones that are on the stack. All instances of the same type will use the same allocator, only called, as I said, like when it's on the heap, not on the stack. And it does not propagate to the members. If you have a class and this class would have members and these members also need dynamic memory allocation, this will not be used. This is only for the construction of foo, not for the construction of sub-objects of foo. Okay, next way, we have custom allocators. Basically, custom allocators, how it works is like you just define your own class. And basically, the minimum that you have to provide is this value type. Then you have to provide an implementation of allocate and implementation of deallocate. This is like templated. And what do we have? We have, you can use multiple instances for the same type allocator. It needs to follow some allocator requirements. Like it's defining the standard, what are the requirements, and you have to follow them. And I mean, it's based on type traits. And the good part here is that several of the traits are optional. And this is making it much easier because basically you have these allocator traits, and this is how the standard library gets all the information about allocators. It goes through allocator traits. Allocator trait is templated by the allocator, and this allows you to get information, the default information of the allocator. And for example, one of these default information would be if it propagates or not. What does it mean? Like when you copy or move a type with the custom allocator, just imagine that you have two types and you want to like assign one to the other one, like two instances of the same type, you want to assign one to the other one. What do you do with the allocator? You also propagate it? Do you also copy it? Yes or not? And this is something that you can choose at the allocator level. You say if that it propagates or not. Now, basically, we have then yet another option. I'm not so sure if so far there's any questions, but okay. Basically, we have polymorphic allocators. This is a part that was introduced in C++ 17. And it makes life much simpler and easier. How it works is that you declare a storage. If we saw from the mental model of C++ that I showed you before, you have a storage. And now here you define your storage. It can be stud bytes or it could be unsigned char. Please do not declare it with char. That is not allowed. Might be surprising, but that's not allowed. And then basically what you do is like you can use a memory resource. And basically it's an allocator that basically you can define behavior. The behavior can be configured at runtime. The functionality is divided basically like into parts. You have the allocator part and the memory resource. And you are kind of like decoupling like the storage from the way that you allocate. And you have multiple memory resources. Like you have multiple ways that you could get the memory. And one thing that time has told us is that most of the people end up using the same type of memory allocations or the same memory resources. Or you want to allocate from the heap, or you do not want to allocate at all, like you just want to forbid it, or you just want to do a monotonic allocation that basically just increments. And there are a couple of more also. And these are included in the standard. It means that you do not have to implement them on your own. And you have this null memory resource that basically what it does is like, if you call an allocate on a null memory resource, it will just terminate. That's, I mean, not terminate, it will throw the but alloc exception. And basically you have another memory resource that is the new one delete, that basically what it does is just, it calls the new that you would expect. I mean, what we saw that with the global new function, that once you replace it, you cannot do anything anymore. Basically, this allows you to call the default new one delete. And now here the thing is that one of the problems is that the polymorphic allocator does not propagate when you do move copy assignment. But the good part, I mean, okay, the good part is that I didn't put it, I think. The good part is that if this vector would contain strings, then it's also used for the inner parts of the container, like a PMR vector of PMR strings, then that allocator also would be used for allocating the memory of the strings. The part that is not so nice about these ones is that if you grab two containers and you do a swap, in case that the allocators, they do not compare equal. And what does it mean conceptually or semantically that the allocator compares equal? Comparing equal means if I allocate with this allocator, I could deallocate with the other allocator. If they do not compare equal, you are not allowed to deallocate with another allocator. It would be like, I take the memory from here, and then I leave it back, give it back to another place. That does not work. And if they do not compare equal, it means that you cannot do the swap, and that isn't defined behavior. That's something that you need to be careful. Yeah, and here I had it like that it propagates to the members of the container. Let's try to recap on the summary here. What I want to show to you with this talk, I'm not so sure how many of you are aware of all the issues or all the things to consider. The point here is that this is not so trivial. But we need to go back. We need to go back some steps. What we want to achieve in the end is functional safety. We want to achieve that if we put a plane on the air, it will not crash. If we have the car, it will not crash. Like, we want to make sure that the user is safe. That is the goal. And that's what we need to achieve. The part that you need to keep in mind here is that on one side, we have the C++ mental model. In C++, we have the storage, we have the objects has a lifetime, the storage have a lifetime. And that's pretty it. And then you have the different storage duration, you have the automatic, you have the stack. With the automatic, you have the dynamic storage duration and the local. But basically, like, that's it. That's pretty it. But on the other side, we have the real world. And on the real world, we have the operating system, we have the standard library, and the compiler. And these things will have an impact on how you do, like, how it behaves. In the end, and this is not to tell you, yes, use dynamic memory allocation, it's also not to tell you, no, don't not use it. But if you want to use it, you should be aware of these challenges, and you should be aware of these potential pitfalls that we talk. We have memory leaks, we have out of memory, allocation, deallocation mismatch, memory fragmentation, non-deterministic runtime, and then we also have the use after free. And it's quite easy that you end up with these same issues, even if you do custom allocators. Like, you have to provide the storage. You might end up that the storage that you provide is not enough. What do you do in that situation? If you try to go fancy on your storage and you start doing like, you might end up re-implementing the malloc. And if you end up re-implementing the malloc, you will have to end up also having the mmap. You will end up having the non-deterministic runtime. You need to tailor it very well to your use case, basically. And I see that I'm a bit ahead of time. This is a little bit what I had. If there's some part that maybe we can just go back to the examples, if there's some part that you want to see in more detail. I would like to thank everyone from the Minix C++ user group that were watching this talk and were providing valuable feedback. And basically, this is what I had to say for today. If you have any questions, that would be the time.